Okay, so now I want to show you another couple of options that you have for notation when you want to define a function. So let's say you wanted to define a function that takes an input value, adds 2, and then sends the result back. One of the common ways you'll see it written is something like the following. You'll see something like y is equal to x plus 2. And in this case, what you're doing is you're using x and y to represent the input and the output values. Okay, so typically we'll say that x is the independent variable because it doesn't depend on the value of any other variable, where on the other hand, y is different. Y is the one that we refer to as the dependent variable, because the idea is you choose a value of x as the input value, and then as soon as you choose a value of x, like look at it up here, let's say you choose x equal 1, well, then that immediately is going to imply that y is equal to 3, right? It forces the value of y to follow suit. If you plug in x equals 0, you're going to force y to equal 2. If you plug in x equals 5, you're going to force y to equal 7, and so on. So that's the idea. X is a representation of x is a variable that represents the input value. So you've got a function just like the diagram I drew at the beginning of this section. You've got x as the input value, but then now instead of using the notation we talked about before, we just let y be the notation that represents the output value. Okay, another option that you have, and you'll see this less often, but if you want to just define a function on the fly really quickly without going and writing a formal definition, you can say something like this. You could also just say, like, let's say we're talking about this function, the one that, and I'll say it just to say it in words, the function that takes an input value, adds 2, and then sends back the result. You can define, another way to define that function would be just to say this: take an input value x and return x plus 2. Okay, so that's another way to write it. And then when you do that, this is really what you're doing is you're just saying it takes an input value and adds 2 to it. You're not giving the function a name at all. So, but that's another option. Okay, so on the next page, which is where we'll finish this section, we're going to take a look at a few more complicated functions, and we're going to find their domains. So, and these principles are going to be important. So whenever you're finding the domain of a function, whenever you see a fraction, right away you know that the denominator cannot be 0, and that will give you a domain restriction. So if you have any fractions in a function, in the definition of a function, and the denominators of those fractions are expressions that involve the input variable in some way, then that's where you're going to get some restrictions to figure out what the domain is. Another restriction you can get is if you have any square roots or any fourth roots, or actually in general any even roots. As soon as you have an even root, then immediately you know that whatever's inside that root must be non-negative. It's allowed to be 0, but it can't be negative. So that forces whatever's inside the root to be greater than or equal to 0. But if you have odd roots, like the cube root, the fifth root, or the seventh root, those will not add any domain restrictions. No matter what's inside a cube root, fifth root, or seventh root, it's always going to be defined everywhere. There's no problem. And same with sums, differences, and products. Anywhere you see a sum, difference, or a product, that won't change the domain at all.